Good afternoon everyone. Thank you for joining Mr. Ish today for today's video on inverse trigonometric functions. If you all think back to the video I presented a while back on regular inverse functions, I mentioned two items. I talked about one-to-one and I talked about range duplication. Very quickly, as a quick review, just to refresh the concept of inverse functions. Remember, functions are functions in general, but special functions above and beyond that can be inverse, and they can be inverse because they are one-to-one in terms of their domain and range values. They are one-to-one. But let's very quickly revisit that topic. If you're talking about a regular parabola, f of x is equal to x squared parabola, and we can put in a couple of table of value points starting from 2, 1 going down up to -1 and -2. If we put a 0 in place of this, y equals x squared, in place of x, we get y value of 0. If you put 1, we'll get a 1. 1 squared is a 1. Same with -1, we'll get a positive 1. Look what happens when we put -2. When we put -2 over here, of course we get a 4, and same with 2. The only reason why I'm bringing this, and parabolas have a domain of -infinity to infinity. So over this domain, you have a range duplication. Look at these values which are duplicated in terms of a horizontal line being able to pass across. It fails the horizontal line test. Here you have range duplication. These two separate domain values each have the same range value, 1 and 1. These two separate domain values, 2 and -1, have the same range value, 4. So that's called range duplication. Anytime you have range duplication, that specific function in interest is not one-to-one, therefore you cannot calculate its inverse. But there's a trick around that. If you are to supposedly change the domain of your function and restrict it, let's get rid of this all-encompassing -infinity to infinity domain and restrict it from 0 to including 0 all the way up to infinity. Now all of a sudden our graph loses this aspect. See, we lose this aspect of our graph, of our parabola. It becomes just a single side parabola, and by doing that we've eliminated these negative values over here, and if we keep proceeding in the direction of positive infinity, you'll never have range duplication. For each specific x value you'll have a specific range value, therefore you will not duplicate your range. And you could have done this in the minus side only and eliminate the positive side values, but again, now with this domain restriction, we've committed our original function such that you can have one-to-one and you can do an inverse calculation. And the procedure for calculating the inverse for any function was to switch the letters around. If supposedly you had y was equal to x squared, you just had to switch the letters around. X became y squared, and then you calculated for that y became root of x. So this inverse was now represented by the root of x. So this was a general procedure for determining one-to-one, determining range duplication, and then finally calculating the inverse. So keep all of this in mind as we proceed through this video with regards to trigonometric functions. Very generally, if supposedly someone gave you this formula right here, sine x is equal to 1 over 2, or someone said tan of some value variable x was equal to 4.2, and someone told you to solve for x, instinctively you would do that easily by means of a calculator, or maybe in some cases you wouldn't need a calculator. Just by looking at this on the top, what would you do? You would take the sine on the other side, right? Let's look at this one over here. You would take sine on the other side, you'd get sine inverse of 1 over 2. You would do that. You'd put 0.5 on your calculator and you do inverse sine function of that, and you'd get 30 degrees. You do 0.5 inverse sine, you get inverse sine, and you get 30 degrees, pi over 6. Here x was equal to 30 degrees. This right here, concept right here, is the inverse function. You can also have written this as arcsine, arcsine 1 over 2. What about this question right here? Intuitively, you take tan on the other side, you write it as tan inverse of 4.2, or you can say arctan 4.2. You put 4.2 in your calculator and you do inverse tan of that and you'll get your degrees. 4.2 inverse tan and you get 76.6 degrees. Your answer is 76.6 degrees. So when we're talking about inverse of trigonometric functions, we're actually talking about these inverses right here. But do not confuse inverse as being a reciprocal exponent. It by no means is that. And when I'm saying that, this is exactly what I mean. If supposedly you see this type of function, cosine minus 1, inverse cosine x, you don't want to be thinking of this as 1 or cosine x, meaning you're doing a negative 1 exponent. You know, normally an exponent of minus 1 makes everything a reciprocal. This right here is wrong. When we're talking about this, we're talking about arccosine. We're talking about inverse cosine. We're not talking about reciprocal cosine. The only way something like this would lead into something like this is how it would look like. You see cosine x, now all of this is to the power of minus 1. Now in this case, you can say it's 1 over cosine x. This is legitimate right here. This right here is true, but this right here is wrong. So keep all of this in mind as we proceed through today's video. Let's look at everything we've been talking about now in terms of trigonometric functions. If I were to draw a very basic sine function, a sine graph, I'm gonna do partly on one side only. You know, the basic trigonometric function is gonna look something like this. And this I'm talking about a sine x. And we can proceed it into this direction right over here. Remember earlier I said normally such functions are not one-to-one unless you restrict their domain. Look at this, you'll have range values duplicating. If I were to continue this line over here, this curve onward over here, this domain value would have a specific range here and it would be duplicated here. This point over here is duplicated exactly over here. One full wave away, it's duplicated right over here. So you have range duplication. But how can we show that a sine wave, cosine wave, tangent wave, actually all these 6 trigonometric functions indeed have inverses. But how can we show that? We can do that by restricting the domain. And I'm going to show you how you will restrict this domain and show that indeed there is no range duplication over that domain. You restrict the sign. We're talking about f of x is equal to sine x. I'm going to show you that this thing has an inverse. If we restrict the domain over here from minus pi over 2 to pi over 2 and we create a table of values, you see the whole sine wave has been constricted to the domain of just 180 degrees, from minus 90 to positive 90. And I'll show you this will be 1-to-1. If you look at possible table points, I'm going to put D over here for my domain and range, or for range. What are some of my points? One point can be minus pi over 2, which is minus 90. Another point can be minus pi over 4, which is minus 45. Another point can be right at the origin. Then likewise, we can have the positive versions of these same points. When we have a minus pi over 2 for a sine wave, we have a range value of minus 1. This is your y value. For minus pi over 4, sine of minus 45, you get a minus 0.707, which will be minus 1 divided by root 2. Sine of 0 is a 0. Sine of 45, you're going to get a 0.707. Sine of 90, you get a positive 1. Look at this. There's distinct domain values and there are distinct range values. Therefore, there's no range duplication from minus pi over 2 to positive pi over 2. That is, from this specific domain, the sine function is said to have an inverse. And you can show that like this. If f of x is equal to sine x, which is same as saying y is equal to sine x, you switch the letters around. You can say x is equal to sine y. You solve for this y. Y is equal to inverse sine or arcsine, arcsine, with a minus 1 and x. Now we've shown you from a domain of minus 90 to a domain of positive 90, there indeed is an inverse function for the sine. And I've shown you here by table of values there's no range duplication and everything is 1-to-1. But let's look at the similar effect for cosine and tan functions, and I'll show you the actual graphs for these inverse trigonometric functions just for sine, cosine and tangent. The reciprocal trigonometric functions cosecant, secant and cotangent are important but will not be discussed in this video. Here is the restricted domain for a cosine function. F of x is equal to cosine x. Normally, sine and cosine have a domain of minus infinity to infinity, but we're talking about restricting domain so we can show that these functions have an inverse. If we restrict the domain of the cosine function from 0 up to pi, you will see that there will be an inverse. And this is how you're going to draw it. You're going to draw only that portion of the entire cosine wave from 0 to pi. And you know it always goes through 0, 1. And it has an x-intercept here at 90 degrees, but then cosine of pi is a -1. And your wave comes out looking like this. This should be right here to pi over 2, which is 90. But look, if you can continue this in all directions, then you'll have that continuous cosine wave. But we're restricting here from 0. We're restricting our domain from 0 to pi. But within this domain restriction of 0 to pi, you have the ability to generate an inverse function for that cosine. And let's show you domain and range values for this specific domain set over here. If we can start over here let's start over here from 0 and work onward. 0, we have pi over 4 next, then we have pi over 2, which is 90 degrees. Here's my 45 degrees. My next 45 degree angle is 3 pi over 4, which is 135 degrees. And lastly, we have pi. At 0 degrees, cosine range value is a 1. At pi over 4, you get 0.707. All you gotta do is cosine 45 on your calculator. You get 0.707. Cosine of 90 is a 0. Cosine of 135 is a minus 0.707. Finally, cosine of pi, which is 180, is a -1. Look over here, the distinct domain values and distinct range values. You have 1-to-1 effect going on over here, 1-to-1. So therefore, you can easily generate an inverse within the domain of 0 pi for cosine function. And look over here. If generally y is equal to cosine x, switch the letters around. X is equal to cosine y. Solve for that y. Y is equal to cosine inverse of that x. Or you can say arc cosine x. Arc cosine and inverse cosine are synonymous. ARC here is synonymous with inverse when we're talking about trigonometric functions. Here, now you know this right here is equal to your inverse function for the cosine. So here I've shown you that cosine within a restricted domain of 0 to pi has its inverse. We will look at the tangent function next, then I'll show you the individual graphs of these, then we'll just look at some practical examples. Let's look at a tangent function in terms of it having a inverse, tan x. And then I'm going to show you the quick table of values for the tangent function. Generally the tangent function has a vertical asymptote at pi over 4, pi over 2 actually, and minus pi over 2. I had a slip of tongue over there. So tangent at 90 and tangent at minus 90, you'll have vertical asymptotes. And the curve looks like this. If we restrict the domain, tangent has a domain from minus infinity to positive infinity, but there are those asymptotes which pop up which break that domain. And I've shown you that in my trigonometric function graph video, how the domain is written for that. But if you restrict the domain purely to minus 90 to positive 90, you can show that this tan curve will have an inverse. We will look at a couple of points starting with minus 90. You have minus pi over 2, and I'm going by 45s here. Minus pi over 4, minus 45, then 0, then pi over 4, and lastly we have pi over 2, which is 90. What do we get? When we have tan of minus 90, we're running along an asymptote, and let's just say we get a minus infinity. When you have a tan of a minus 45, you're technically going to get a minus 1. Just do tangent of minus 45, you'll get a minus 1. Tan of a 0, clearly a 0. Tangent of 45, you'll get a plus 1, right over here, plus 1. Tangent of 90, you're so close to that asymptote, we can say we're getting an infinity. Look, clearly distinct domain values and clearly distinct range values, 1-to-1. No duplication of range, therefore tangent in this domain, restricted domain, you'll have an inverse. And you can see again, f of x is equal to tan x. Switch the letters around. X is equal to tan y. Solve for y. Y is equal to arctan or inverse tan of x. Here's our inverse function for tangent. You can do likewise the same for cosecant, secant, and cotangent, but I won't. I just wanted to spend some time showing you how by restricting the domains for sine, cosine, and tangent, you can demonstrate their inverse functions. And inverse functions are shown like this. Arctangents, arccosine, arcsine, or in this form with the -1. Do not confuse this as a -1 with a reciprocal effect. Let's look at specific graphs of these three functions when they are in their inverses. Then we will look at some practical examples. Here on the board, I'm showing you graphically the inverse sine and cosine functions, arcsine and arccosine. And you can see, and we'll highlight some of the important points. If you take the inverse of the sine function and you graph it, you get something like this, again with a restricted domain. But look, the x-axis values become exactly what you are plugging in as your domain. The range values is what you get as your angles, which makes sense. Remember that example I said sine x is equal to 1 over 2 and you solve for that x? Well, it makes sense. You're putting in what would normally be your answer to determine what your angle was. So your angles here represent the y-axis, your range values, your outputs. If you look at this inverse sine function, you know it extends from a -1 to 1 because we're talking about restricted domains. And the output values extend from -90 to +90. So the domain is very clear over here. It's -1 to +1. All points included along this line from -1 up to 1. And look at the range. It goes no lower than -pi over 2, but it goes no higher than pi over 2. Again with square brackets. Lowest limit and highest limit, -pi over 2 to +pi over 2. Similarly for cosine, again, when we're talking about inverses, our inputs, our domains are usually the values which you would normally have gotten when we're dealing with regular functions. And our outputs here, which are our range values, end up being angles. Which is why here along the x-axis we're getting what we would normally have here being angles, but we're getting numerical inputs over here. Angles represent our outputs, our range. But look at this specific curve over here. When you draw it along that specified domain, our domain is essentially again from -1 to +1. It's a restricted domain where what were normally the outputs are now your inputs, and those inputs are representing your domain. And look at the range. It's going no lower than a 0, but it's going no higher than a pi. A restricted domain and a restricted range. 0, pi is that range. Keep all of this in mind. If for nothing else but other than just understanding how the one-to-one functions play out in terms of their actual graphs. I want to show the tangent function before we start proceeding with some examples. The arctangent function, the inverse of tan, is easy. Again, the lower limit is a -pi over 2 and the upper limit is a pi over 2, which is 90. Here your outputs are basically angles again, because you would normally be using these inverse function calculations to determine an angle. You'd have a numerical answer and you want to determine what angle represented that, which is why angles represent here the range values. The answer that you're trying to use to reflect the angle that it is are your domain values. So how does this look in terms of the inverse tangent function? You get a curve for the inverse tan, something looking like this. Remember the original tangent function which I showed you looked something like this. Within that asymptote like this, you basically have the inverse of this, but this in this format. The domain is actually pretty easy. Here you have a domain going all the way up to -infinity and going all the way on the other end to +infinity. No more square brackets. Up to but not including. And the range. Range never goes below -pi over 2, never touching it because there's an asymptote over here, but never going above up to 90 pi over 2. Up to it but never touching it. Easy domain, easy range. So these are basically just the graphs of your inverse trigonometric functions, the main important graphs that you should be aware of. Keep everything I've told in mind, especially with regards to one-to-one range duplication, how you've had to restrict the domain to demonstrate the one-to-one effect of sine, cosine, and tangent. I want to show some examples. Let's look at a classic example. You see this in front of you. Sine, inverse sine, root 3 over 2. Your goal is to determine the angle which is represented by root 3 over 2. You can also say this as arcsine root 3 over 2. How you would have looked at this originally would have been f of x or y was equal to sine of some angle. But that sine of some angle, which was your y value, was originally root 3 over 2. Now you're basically working backwards. Sine of what angle gives you root 3 over 2? You can do that easily by determining the inverse sine of root 3 over 2. So now you're working, originally you're used to working in this way. Now you're basically working in this way. You gotta learn to see and work in both ways. Inverse sine of what angle gives you root 3 over 2? Look at these. These look like the trigonometric ratios. If you have a right triangle, you know sine is always opposite over hypotenuse. At what angle can you get a root 3 opposite to it? You can get from a 60 degrees, 60, 90, 30 triangle with root 3 opposing the 60 angle. So just by looking at that, I know my angle should be pi over 3, which is 60 degrees. So in arcsine, root 3 over 2 is equal to 60 degrees. You can do this on the calculator, right over here. Write 3 and root it, divided by 2. Hit the inverse sine function. Sine, the shift and then the sine button. I get 60 degrees. Okay, so you're looking at these functions on your calculator. You got your sine, you got your cosine, and your tangent. You're looking at this right here. Sine minus 1, cosine minus 1, the tangent minus 1, the inverse sine, the arcsine, the arccosine. That's how you're going to see your questions. Let's look at something with relation to the tangent. Let's use this word, arctan. Let's bring a number over here, minus 1.33. What angle, if you were to tan it normally, would give you an answer of 1.33? So listen to what I'm saying. What angle, if you were to tan that angle, take a tangent of it, you get a minus 1.33. You're thinking inverse over here. You're thinking backwards. So you're going to do tan inverse 1.33 minus, right? Take 1 point, you can't do this in your head because we're not talking about trigonometric ratios here. Write 1.33 on your calculator, minus it, inverse tangent, shift tan, and you're going to get a minus 53.06 degrees. A minus 53.06 degrees. But what does that really mean? If you're looking at a quadrant over here, you're going minus in this direction, clockwise. Minus 53.06. You can do 360 minus 53.06. And what do you get? You get 306.9 degrees. 306.9 degrees. If you do 306.9 degrees and you tan it, you should get a minus 1.33. I got 306.9, I'm going to do tangent of it, I get a minus 1.33. So you can work frontwards and you can work backwards simply by understanding the concept of inverses. I'm going to show you some types of questions that you will see play out in calculus. The question is this: you're asked to find the exact value of something which looks like this. Taking the tangent of arc cosine 2 over 3. Looks a little complicated. You got two things over here. You have a function, an inverse function within a function. You can think of this as a composite function, but this is how I would recommend you to do this. Always start with a 90-degree triangle and designate one side as your theta or x, whatever variable, and then you look at the definition of cosine. You know cosine is adjacent or hypotenuse. So plug those in. What's my adjacent here? It's a 2. Remember, it's always adjacent or hypotenuse for cosine. What's my hypotenuse? 3. You got to calculate this using the Pythagorean theorem. A squared plus b squared equals c squared. And you know what you're going to get over here. 3 squared minus 4 squared, you get a root 5. All you've done now is you've used this to map out your triangle. Now all you have to do is find the tan of this. But the tan of this is basically based on the tan of theta. This whole over here could have represented a theta over here. So what's tan theta? It's equal to opposite over adjacent, root 5 over 2. Now the question was to find the exact value. This right here represents a good enough exact value, or you can take your calculator and do square root of 5 and divide it by 2 and get a decimal answer. You can get a 1.118. Here's another exact value. But this you'll see quite a bit play out in calculus. Tangent of arc tan minus 5. Looks a little complicated. but it isn't. Think about this again in terms of a right triangle. Draw your theta. Look at the definition of tangent, arctangent. What's your definition of tan? You know what it is. It's opposite over adjacent. Let's just put a -5 and let's put a 1 over here. Do we need to calculate this side over here? No, we don't, because we're not looking at another function which will even require hypotenuse. So what's tan of arctan is exactly tan of theta, which is what? -5 over 1, which is what? -5. So tan of arctan -5 was in itself -5. Here's your answer, -5. What if the question stated, find this, secant arc tan -5. How would you go about doing this? Now in this case you better find a square plus b square equals c square. I'm going to bring out my calculator. You have 25 plus 1, you get root 26. Actually I didn't really need my calculator for that. But I filled all the deficiencies over here. Now all I have to do is determine secant of theta. What's secant of theta? Well, it's the reciprocal of the cosine function, which will be 1 over root 26. Therefore secant will just be root 26 over 1, which is what? Root 26. How about using the same example if the question was cotangent of arc tan -5. Here you've already done this part. You remember you're using the inner part to map out your triangle. Then you're actually determining the part outside. What's cotangent of all of this? Well, it's going to be adjacent or opposite. It will be -1 over 5. So that's cotangent of arctan -5 is -1 over 5. So that's another question done using this example. I want to show you an example or two which will involve variables instead of just numbers. You have a question presented to you which looks like this. You have to find the sine value of arccosine 3x. Remember, arc over here implies inverse. It could be just cosine -1 3x. You can just look at this as cosine to the power of -1, but this -1 here represents an inverse. Okay, you can look at it in exactly that way of 3x. Again, when you see questions like this, and they'll pop up quite a bit in calculus, your first goal should always be to use this inner part to map out your triangle. And you know we're always talking about a 90-degree triangle unless otherwise stated. Just put a theta somewhere over there and look at the definition of the trigonometric function within your parentheses. We have a cosine. Cosine is always what? It's adjacent over hypotenuse. We do have a fraction over here. Always look at things in terms of fraction. You have a 3x over 1. Adjacent over hypotenuse. Here's my adjacent. My hypotenuse is 1. And you got to find that missing side. A square plus b square equals c square. You know what this will be? It will be 1 minus 9x square root. Remember, if you do a square plus b square equals c square and you solve for that missing side, you'll get a square root of 1 minus 9x square. Now you have everything you need to find the sine of this. The sine of this will be opposite over hypotenuse, which will be square root of 1 minus 9x square over 1. This over 1 is kind of meaningless. So your final answer will just be the square root of 1 over square root of 1 minus 9x square. How about if the question stated this? Find the cosecant of arc cosine 3x. Again, you would have done all of this procedure to map out your triangle, get the missing side filled, and just do the cosecant of that. Cosecant would be hypotenuse over opposite, which would be 1 over root 1 minus 9x squared. And you can rationalize this, take all of this, multiply here and here, and present a rationalized answer. But this right here is an acceptable answer. So look at how the procedure is. Always starting by looking at the item in the parentheses, working it to map out a triangle, filling in the missing sides if indeed it's needed. If supposedly you have to have it for the function which you're looking at, then you look at the function and calculate that. Here's a question, cotangent of arc. Let's make this interesting. Cotangent of arc cosecant 1 over x. Look over here always. Use this to map out your triangle. I map it out. A 90-degree triangle, put a theta. Look at the definition of the function you have here. The inverse you have an inverse, but you can use inverse to map out your triangle. We're talking about a 1 over x, but we know the definition of cosecant is hypotenuse or opposite. Hypotenuse over opposite. See, here's my hypotenuse and here's my opposite. Sine would have been x over 1, but cosecant is 1 over x. Fill out this missing side. A square plus b square equals c square. B square must be equal to c square minus a square. 1 minus x square, and then you take, of course, the square on the other side becomes a root. Now all you got to do is find the cotangent. Cotangent is equal to, with everything always in relation to your theta, the cotangent would be your adjacent over opposite. It would be square root of 1 minus x square over x. You'll see this quite a bit in calculus. Lastly, question this. You have secant of tangent x. Someone tells you secant of tan, determine the exact value of secant of tan x. And this right here, instead of putting arctan, I'm putting it inverse tan, because we're looking at inverse functions over here. We can do this. Let's map out our triangle over here. Put our theta, use the definition of the function over here to map it out. Tan is always opposite over adjacent. X over 1. You know what this will be? It'll be 1 plus x squared. A squared plus b squared is equal to c squared. The secant. What's the definition of secant? It's going to be hypotenuse over adjacent. Everything with regards to your theta. Hypotenuse over adjacent. And the secant value here would be 1 plus x squared over 1. You can eliminate this 1 over here, and here will be your clear and correct answer. Square root of 1 plus x squared. So keep all of this in mind with regards to inverse trigonometric functions. They're easy. Graphing them is a little difficult because it's a little bit of a twist in your mind. You have to try to see how you can see that inverse play out. But by restricting the domain, you can get the inverse of each of these 6 functions. And then be specifically aware of how to calculate these type of questions because they'll show up. But remember, you've been doing inverses all along. If someone gave you a value and you had to find the angle, you were using an inverse to determine that on your calculator all along. Now you're just thinking of it in a more formal sense. I hope you enjoyed this video. Thank you for watching. Please like, subscribe and share. Have a nice day.